So the review here is not meant to be super in-depth. It's really just to touch on what are the most important points. So I call this page I put together for finals my guarantees because if I can fit it on the final, it will be on the final. I can guarantee I will try to put these things on there. They may not all fit in the amount of questions that I want to ask, but these are the main things I would be studying if I were you. It's also not a guarantee that this is the only stuff that will go on there, but if you look at the number of topics listed, it's kind of hard for me to fit anything else. So it's a pretty good crash course of what the most important things are from each chapter. So for chapter 21, the main things are just how something can become charged, which is through friction. You rub two things together. Through contact, which is just you touch one thing to another, works best for conductors. And then through induction, which is a non-contact way of, it's usually just inducing charge, so making charge separate like that. But as soon as you take the PVC away, the charge will return back to its sort of equilibrium position, unless you do something to allow some of the charge to leak off and leave a net charge on there. And then that would be a charge created through induction. Um, Created's not the best word because really charge can't be created or destroyed. It is conserved. That's another important thing, but hopefully one that's pretty intuitive. And then quantization of charge. So that's just that it's got to be a multiple of the electron charge is all quantization means. You can't get 1.5 electron charges. You can't get 1.5 billion electron charges. It's got to be a whole number. Coulomb's law, not in the sense of finding stuff like with full-on vector addition, but just if you have some charges in a row, like in this picture, because we'll save the vector addition stuff for electric fields. So remember, Coulomb's law is about electric forces between different charges, and you would find them through your usual net force. If it's to the right, it's positive. If it's to the left, it's negative, sort of thing. The only new bit is Coulomb's law itself, the expression for that force. So it's similar to how in physics 1 you have friction. It you would write as Fs or Fk, but then you may need to know that it actually is coefficient of friction times normal force. Here you would write it as F1 on 3 or F2 on 3, but you would actually need to know how those forces depend on the charges and the distances. That would be an extra step involved. For chapter 22, the net electric field, it is just regular old vector addition, same as always, including in physics 1. The new stuff about it is how you define the directions of your vectors, and that is the bit that I think gets messed up the most often. So say you have some arrangement of charge, like in this picture, or just so we can kind of see a new picture for this. Say we got this picture where we got a positive charge here, negative charge here, positive charge here. We'll call them charge 1, 2, and 3. How you come up with the directions of your electric field vectors to find the net electric field is by pretending the point you're interested in is a little positive charge. That's our test charge concept. So we pretend there's a little positive charge there. We don't need there to actually be one because that's the point of the electric field. It exists even when there is no charge other than the ones creating it, meaning all these other ones present. But to find the direction of that net field, let's pretend there's a little positive charge at that dot. In that case, charge 1 would repel it, and so we would say the field due to charge 1 is downward. Charge 2 would also repel it along the line joining them. So we would say field 2 is like that, while charge 3 would attract them also along the line joining it to the dot. And so we would say field 3 is also downward. From there, you do your vector addition, meaning you find the components of each of those fields, your x and y. The only one that has both x and y components in this picture at least is E2. So it's got an x component and a y component. And you would find those through the usual trig. If you know this angle theta, then the x component is E2 cosine theta, and then the y is E1 sine theta. If they happen to be pointing left instead of right, it's negative E2 cosine theta, and down instead of up is negative E1 sine theta. Usual vector addition stuff. The only new step here is, again, how E depends on charge and distance. So you would substitute that in after doing the vector addition steps, which you're seeing me do for that original picture up here. And then you finish it out as usual vector addition by finding the magnitude with your Pythagorean theorem. That's really the main thing from chapter 22. There are questions about, charged disks and charged whatever, but the main thing I'm looking for in that chapter is finding the net electric field, and that could take up a pretty big chunk of what I could even ask for the chapter because it takes so long to do those types of questions. So I don't want to dwell on that chapter super long. That may be the only question for that chapter. If there is another one, it would be a small concept related question. Chapter 23, the main thing here is, of course, Gauss's law, but specifically that problem for a cube or some sort of box shape where you find for a particular electric field. That's what I'm kind of saying here. It'll be some components for each bit of the electric field. I want you to find the flux through a certain cube, your Gaussian cube, for that field, and then use that to find the charge enclosed by that cube. So remember, we break it into steps, one for each face of the cube. You find the flux through it through your dot product rules, which is your I dot I is 1, J dot J is 1, K dot K is 1, and then every other kind of dot product is 0. And then you add all those fluxes up, and then you set it equal to charge enclosed over epsilon naught. That'll let you find the charge enclosed. So the problem like that from the first exam is pretty much what you could expect, or the ones on the practice. There is that one that caused some trouble on the first exam, which was I've got some kind of charge inside of a shell. And so in this picture, for instance, I've got a little positive charge, plus 5e. And the shell is, let's say it has a certain net charge to it. In this picture, it's plus 7. So those would be your givens, what charge is in the middle and what charge is on the shell. You got to figure out how much of the charge on the shell is on its inner surface, so here, versus its outer surface. How you do that is you come up with a Gaussian sphere that's inside the shell, within the material of it. The reason you choose that as your Gaussian sphere is that inside of a conductor like that, the electric field is 0, and so the flux through that particular Gaussian sphere is 0. That also means the net charge enclosed by that sphere is 0 because of Gauss's law. This right here. If the left-hand side is 0, because there's no electric field inside the material of the shell, the right-hand side is 0. So the net charge enclosed by that shell is 0. But we see that there's, in this case, positive 5e charge in the middle. That means to come up with a 0 net charge, there must be negative 5e on the inner surface of the shell. So that would be the first part, how you found the charge on the inner surface. To get the charge on the outer surface, you just see what you need to add to that to get this net charge, because that's the total charge on the shell. Well, if I need a net charge of plus 7e, and minus 5e is on the inner surface, I gotta have plus 12 on the outer surface to get a total of plus 7. So that's your two steps. For the inner surface, it's about Gauss's law. For the outer surface, it's about conservation of charge, that the total charge on the shell has to be the same as originally. It just redistributed when you put the charge in the middle. Chapter 24, net electric potential. That's the one that's like net electric field, but it's scalar addition, regular old addition. And that's awesome because it's so much easier than the electric field stuff. The important thing is to just not mix the two up. So for V, the electric potential, you will want to do regular addition like this. For E, the electric field, that's where all the vector addition stuff is. That's another thing worth pointing out is the kind of common confusion between E, F, U, and V. This is field, this is force, this is potential energy, and let me rewrite that V because it looks like a U. This is potential. They're all related to each other in a way that you can see like the full details of at the end of chapter 24, I believe. It's that little table that says like a summary of all the math. But just think of E as the force per charge and V as the potential energy per charge. The force itself is F, the potential energy itself is U, but if you look on a per charge basis, meaning divide by, say, a test charge, that's how you get the other one. And the reason we do that is so we can sort of, instead of thinking of two charges, an interaction between two things, we think of just one charge and it's producing a electric field and electric potential. Okay. That's also a good place to mention for your cheat sheet. It might be a good idea to have a table that is 3 columns, quantity, symbol, and units, because we've talked about a lot of different quantities over the course of the semester. For instance, the electric field. Its symbol is E, its units are newtons per coulomb. And you just do that for as many quantities as you think you might mix up. Some common ones I see are things like capacitance. It is C. I don't have enough space here to write it out, but capacitance C, that's the one that's in farads or microfarads. If it's written that way, that's 10 to the negative 6 farads. I see that mixed up with charge a lot. Charge is Q and is measured in coulombs, and I think it's this that really causes the confusion. The unit for charge is coulombs, abbreviated C. The variable for capacitance is also C. If you're doing equations, you're trying to find the right equation, and you see capacitance, you're looking for C in an equation. If you're looking for, or given charge, you're looking for Q in that equation. And so on this previous exam, there was a question about finding the, I think, charge on the plates of a capacitor or something like that. And a lot of people lost points on that because you missed the last step of relating capacitance to charge because you assumed the value that was given was the charge when it was actually capacitance. Something along those lines. Okay. Energy conservation, just like on exam 2, you'll be given some kind of picture with equipotentials. And I just ask you, okay, we launch a charge from such and such to such and such point. Tell me, does it speed up, slow down, not change speed, and by how much, which you can find with the conservation of energy. So just knowing those basic properties of equipotentials is good. The properties are, let's see, fields point from high to low. So in this picture, the electric field is sort of high to low, also always perpendicular to the equipotentials. So downhill in that sense. The other big thing is that positive charge creates high potential, negative charge creates low potential. Positive charges are hills, negative charges are valleys. If you put a little charge into that potential region, like this one here, if it is a positive charge, it likes to go downhill, high to low, meaning it will speed up as it does that. If you put a negative charge in there, it would slow down if you tried to send it from high to low potential because they like to go low to high. Those are kind of your main properties for equipotentials. 26, the main conceptual thing was just the directions of stuff. Drift velocity is the direction that charge is actually moving, whether positive or negative. The electric field, current density, and current, these things down here, they could point in the direction the charge is moving if it's positive charge, but if you've got negative charge moving, then by convention, all of these things still point in the direction positive charge would move. That's just because we had to pick either positive or negative charge as our like benchmark for the motion of other charges. And we went with positive, probably a bad call historically, but it's what we're left with. Calculation-wise, how resistance relates to those geometric properties, and then the definition of resistance. So remember that this thing is not Ohm's law. Ohm's law is that this ratio stays the same when you change voltage. So if I increase voltage, current usually increases right along with it so that the ratio doesn't change. That's what's special about Ohm's law. This whole thing is just how we defined resistance in the first place. It's just a name that we gave. So questions where you might have to sort of juggle around both of those quantities. Chapter 27, pretty straightforward. It's series and parallel resistors and or Kirchhoff's rules. I'd say probably for a problem in this chapter, any question you're given could be solved using either. So I would give you the option of you can solve this problem using series and parallel rules or Kirchhoff's rules. You're not going to have questions separately about both. And then there may be a concept question just about what does series mean, what does parallel mean, that kind of thing. 25, it's out of order, but that's the order we ended up going in. Similar things for capacitance compared to what we just said about resistance. It's those two expressions. The one on the left is just a way of defining capacitance, charge per voltage. But the idea is that capacitance doesn't actually change if you change the amount of charge on your plates. So it's easier to see that if you look at Q over V, that's similar to R equals V over I. If I change one, the other changes right along with it, so that the capacitance itself doesn't change, unless you change something over here. You change the dielectric that you have in between the plates, you change the size of the plates, or you change how far apart they are. Those can change capacitance, but just changing the charge or voltage does not affect capacitance. And that sort of plays into this next bit. If you add a dielectric, what happens to that stuff? That's the water tower analogy. If you have an isolated capacitor, you disconnected it from everything, charge cannot change. If you have a capacitor still connected to the battery, voltage cannot change. And those are sort of your guiding principles to figure out how the rest of that stuff changes. Series and parallel capacitors, I think I would lump in with RC circuits, meaning I might give you an RC circuit where you've just happened to have two capacitors that are in series, and you just got to replace them with one single equivalent capacitor as usual, and then you're back to a regular RC circuit. And then I ask you something about that circuit. For instance, how long it takes for it to charge up, how much charge is stored, or conceptual trends. This stuff down here. What happens conceptually over time. And what that means is, for RC circuits, you can usually expect me to ask about the simple equations, these ones, not the ones with the exponential stuff. If you find yourself using one of those, you're probably digging yourself a hole that's going to be hard to get out of because it's not fun to do that math. Let's try and solve for stuff that way. I'm usually just testing for the basic concepts of RC circuits because that's all there's time for on this exam. Almost there, chapter 28, first right-hand rule. So that's the one where your thumb is velocity, fingers are field, and your palm is the magnetic force. I could give you probably any two of those and ask for the third. You just got to remember that that's what the first right-hand rule is about. And I've got a little sort of guide here. And then I could just ask, all right, how will that make a charge move, like on the last exam? if I have a charge moving a certain way in such and such magnetic field, what kind of path will it follow? Circular path is the answer, but also you may need to sketch out that circular path. And what I would see a lot on the previous exam was you'd get the circle, but you'd forget that the force that you found, the magnetic force, has to be centripetal, has to point towards the center of that circle. And that tells you there's pretty much only one circle I can draw here that would be correct. Because FB has to point towards the center of it. Additionally, V has to be tangent to that circle. So I would see ones like, what did I see? Sometimes it's going the other way, which doesn't make sense because that would be FB pointing upward. But I also saw ones that went like this, which then you've got your velocity and your force sort of flip-flopped. So just remember to draw the correct circle. FB should point towards its center, and V should be tangent to it. Okay. I think that's the main stuff for 28. Maybe the force on a wire, but it's the same kind of questions. Hall effect, I won't put on there. I'll save you that heartache. So mainly just the forces stuff. And chapter 29, second right-hand rule, which is the harder of the two right-hand rules because it's got three, I guess the first one sort of has 3 steps, but this one also has 3 steps and it's easier to mix them up. Your thumb points in the direction of current, your fingers grab onto the wire, and that tells you how the magnetic field wraps around it. But if you want to know the direction of the field at any particular point, you got to think about which direction is tangent to that circle that wraps around the wire. And that's what I've got shown here. So if you've got a current flowing up as shown, you grab it, your fingers wrap around in the circle like that. On the left side of the wire, that would mean the field's poking out of the page. On the right side, into the page. In front, it would point to the right, and in back, it would point to the left. So practice those if you're still not used to the right-hand rules. I guess one more thing for chapter 28 that I forgot is just remember if you've got a negative charge, it just flips stuff. So instead of away from your palm, forces towards your palm. So don't forget that last step if you happen to have a negative charge like an electron. Okay, back to chapter 29. This question, I think, tripped up a lot of people on the last exam, finding the net magnetic field. In that case, it was if the field is equal to 0, what has to be true. If you have 2 things creating magnetic fields, for instance, a solenoid and a loop of wire, if the net magnetic field is 0, it's because those 2 individual fields are canceling each other out, meaning if one's pointing into the page, the other is pointing out of the page. And also that their strengths are exactly equal to each other at the point in question. So on that last exam, one of these was the field created by the solenoid, the other was the field created by the loop, and then you would just put in your expressions for both of those fields. So for the solenoid, it was mu naught n over L I1, let's say, and for the loop, mu naught, say I2 over 2R. And this is your condition to have 0 net magnetic field, because it's hard to see that from this equation, but we could also write it as B1 minus B2 equals 0. And that's what shows you one of these is poking one way, the other's poking the other, hence the negative. And I think that is it. Chapter 30 is again not on there. There will be multiple bonus questions, and you can have front and back for your cheat sheet. Are there any questions?
Could you, from the review, could you do like a vector from chapter 21 question?
Okay. Chapter 21 or 22?
One for each one.
Okay. So remember for 21, vectors are in the sense of vectors along a straight line, not the full vector addition stuff. So let's look at one like this. 3 charges along the x-axis, the mass of the this charge is 4 times 10 to the negative 9 kilograms. Find the magnitude and direction of the acceleration of that charge if the other two charges remain fixed. So I'd first think about what the other two charges would do to it. The one over here on the left, it would attract the charge in the middle because they have unlike charges. And so if I number these off, that's a good tip, is to number them off. It helps keep things straight. Charge 1 would attract charge 2. So this is the force charge 1 exerts on charge 2, pulling it to the left. Okay, now what does charge 3 do to charge 2? Well, it also will attract it because they are unlike charges. So this is the force 3 exerts on 2. To find the net force, I usually call right the positive direction, left the negative. So the net force is going to be, depending on how strong these two forces are, either to the right or to the left. I don't actually have to know, I can calculate it out. So it'll be F3 on 2 minus F1 on 2, because F3 on 2 is to the right, F1 on 2 is to the left. Then I put in Coulomb's law. So this is between charges 2 and 3. And then I need the distance between those two. Call it R23 squared. But I just realized that that's this distance, and it's about 6 meters. So that's what I'll need to put in here in a bit. And then K, Q1, Q3, and over R13 squared. Oh, sorry, Q1, Q2 over R12 squared. Because it's the force between charges 1 and 2. And that will be this distance, which also happens to be 6 meters. So from there, I would get some expression after putting all that stuff in. I'm going to see if I can just guess which direction that force should be. So it looks like since this charge is larger than this one, it will exert the stronger attractive force on the charge in the middle. And that means that the net force on the charge should point to the right. So I'm guessing, without calculating, this will come out positive for my answer, meaning to the right, and then it'll be some value in newtons. And then it asks about the acceleration. That's going to be the same direction as the net force. You just divide by the mass of the charge in the middle. And so it will also be a positive number, meaning a rightward acceleration, some number meters per second squared. And the actual value is, I think, in the solutions for this. Yep, comes out positive, meaning to the right. Okay, for chapter 22, so two charges are located on the x-axis, one at such and such distance, it's positive. That's really the main thing I'm looking for right now, is just what kind of charge we've got. Charge 2 is also positive. Charge 3 is positive. Charge 4 is negative. Because that's all I need to be able to start looking at the direction of the net electric field. They want to know what it is at the origin. So what I do is I pretend there's a tiny little positive charge right here at the origin. That's my test charge. I say, okay, what would the direction of the force on that little charge be due to all these other charges? Well, charge 1 would repel it since they are both positive. So I would say E1 is to the left. Charge 2 would also repel it, meaning push the charge in the center away. So E2 is to the right, because that's what would happen to the charge in the middle. Remember, always focus on what's going to happen to it, not what it'll do to other charges. Charge 3 would also repel this little test charge, pushing it away. So E3 is down. And charge 4 would attract a little positive charge, pull it towards charge 4. So this is E4. So that's my directions for stuff, and that makes it pretty easy to find the net X and Y components of the electric field. In the X direction, I have E2 to the right, I have E1 to the left. In the Y direction, I have E4 upward, E3 downward. Only now do I actually care about Coulomb's law, how I find E1 through E4. So E2 is K Q2 over R2 squared. E1 is K Q1 over R1 squared. I'm putting absolute values because I've already looked at the direction bit. I don't want to double account for it. Q4 over R4 squared, and then K Q3 over R3 squared. Those will come out to some kind of values. Whatever values those are, I will use to find the magnitude of the net electric field by saying Pythagorean theorem. E net x squared plus E net y squared. If I wanted to estimate the direction of the net electric field, in this picture it's not super clear because we got stuff pointing all sorts of directions, but we could say, okay, charge Q1 and Q2 have the same value, and they're also both the same distance away from the charge in the middle. That's going to mean that E1 and E2 are the same size, so they will cancel each other out for this particular problem. Charge 3 and charge 4 are different values, and that makes it trickier, and they're also at different distances. So one thing would lead to me thinking charge 4 creates the stronger field because it's got a bigger charge, but it is also further away from the test charge. And the question is, which of those wins out as far as determining the strength of that field? I don't actually know. I may be wrong. I don't remember the answer here, but my guess might be that since it's further away and the field depends on the distance squared, maybe E4 is a little bit weaker than E3. Maybe it's actually a tiny bit smaller than I drew it, and E3 is more of the dominant field. And then I would think the net electric field points downward. That is a guess. If I did the math, I may actually get the other answer, but let's see. Okay, so it points upward, and that is towards E4, so I was actually wrong. E4 is the stronger between E4 and E3. So that's just a sort of off-the-cuff way of guessing at it. You may be wrong, but the calculation will prove it out either way. We did get it correct that E net x is 0. This one is the one that you'd probably need to calculate to be absolutely sure of. Maybe just for the sake of mentioning one where it's at an angle, I won't do this full problem, but I'll just say, okay, charge 1, it's at an angle to the origin, which is where we want to know the net electric field. Well, I pretend there's a little positive charge at the origin. Charge 1 is positive, so it will repel the little pretend charge at the origin, meaning E1 points away from charge 1. Okay, I need to find the components of that to be able to say how much of it is along the x and how much is along the y. So if this angle is theta, this angle is also theta, and then I can split E1 into x and y components. It'll point down and to the right. With this as my theta, this would be E1 sine theta because it's opposite that angle. It will be positive because it points to the right. And then The y component will be E1 cosine theta, but it's negative because it points downward. And so when you do your net x and y components, it'll be all the stuff from the other charges, 2, 3, and 4. But then for E1, we would have plus E1 sine theta, and then minus E1 cosine theta. And then you just proceed as normal. Sine theta and cosine theta are just little things that get tagged on to your usual stuff for E1, which is putting in KQ 1 over R1 squared. All of that goes into E1, and then you just multiply by sine or cosine of theta. Otherwise, same type of problem.
So for the stuff regarding series parallel resistors and capacitors, it'll be like the previous exam where it's just find the equivalent resistance, capacitance, and finding the charge or voltage working upwards from there.
Yes, so it would be probably that two-step thing you just mentioned. First, you find the equivalent value of either resistance or capacitance. I would focus on studying for resistors mainly, because I'll make it easier for capacitors. And then once you've found that, like you said, you work from that simplest circuit back up to find the voltage across one of the resistors, the current through one of the resistors, or the power dissipated by one of the resistors. It's the same thing. You just have to be very careful about making sure you know the voltage across and or the current through the resistor you're being asked about. Not just any old current, not the battery current, not the battery voltage, unless those happen to be what's across that resistor. Otherwise, you got to do some calculation to make sure you get specifically that voltage and or current.
Alrighty, thank you.
Mm-hmm. Okay. Other questions?
You said there would be some questions regarding the like charge within a cylinder from the earlier chapters and whatnot.
Within a cylinder, like Gauss's law?
I believe so, yes.
Okay, yes, but not within a cylinder. It would just be the one that's at the look at the very last page of the chapter 23 notes or the question on exam 1 that's about a charge inside of a shell. That's the type of question I'm getting at, and it pretty much runs the same way no matter how it's set up. So just get that algorithm down and you'll be fine for that type of question.
Okay.
Yep. And look at the conceptual ones related to it because I may swing conceptual on that just because I'm already asking that really long calculation question about the cube.
Can you do number 12?
Sure. Before I do, I will say for this one, practice packet is good too. The exams themselves are really good to look back at because I treat the final as like, here's a redo for the exams. They'll be similar questions to previous exams. If I didn't ask it on a previous exam, it's less likely to show up. I could ask some variants that aren't quite the same as what was on the previous exams, but it's supposed to be in the same spirit as those. So if that helps you focus your studying, good. Okay, so positive charge is uniformly distributed on a semicircular rod. What is the direction of the electric field at point P, the center of the semicircle? So how I would look at this, there is a calculus way to do it, which is to do that integral adding up all of the little dE's, which is the integral k dq over r squared, and then you just have to figure out how to set that up so that you can actually do the integral. I wouldn't actually bother with all that here. I would just kind of look at or imagine this ring or rod as a bunch of little charges, because that's the idea of the integral in the first place. Pretend you're splitting this whole thing into a bunch of tiny pieces that each have a little bit of charge on them. And then I just look at, okay, let's start with this little, I'm going to use red, this little charge right here. So what would this charge up here do to a little positive test charge sitting at point P? Would it attract or repel it?
Repel it.
It would repel it. So if I call this charge 1 of technically infinitely many charges, but it just depends how much I subdivide this rod, that's E1. Okay, I could move on to the one directly adjacent to it, but symmetry says the idea that I've got kind of the same thing going on the other side. It's maybe a better idea to look at this one next and say, okay, same thing's happening just the other way. And both of those charges are the same distance from point P and have the same amount of charge because it's uniformly distributed over the rod. If this has the same length as this little segment, they have to have the same amount of charge on them. And that means that the fields cancel. Okay, so apparently those contribute no field whatsoever. That doesn't mean the field there is zero. We just gotta ignore those, or we can't ignore those. So now we move on to the next little bit. We'll call this 3, and then it'll make sense to call this 4. Again, that symmetry idea. Well, it's still a positive charge. It would still create a field that points away from it because it would repel the charge at point P. So I'll call that E3 and E4. There's no reason it should be stronger than E1 or E2. That's not why I drew it bigger. It's just so I can emphasize for these ones. Okay, and this one up here should be the same strength, just pointing kind of the other way. Now I see more of what's going to be happening for the rest of the ring, which is, if I break those two into components, E4 points to the right and up. E3 points to the right and down. Those up and down components will cancel each other out. They should be the same size, but they're in opposite directions. But those rightward components are in the same direction, so they add, meaning the net field due to little bit of charge 3 and little bit of charge 4 should point to the right. They didn't cancel like 1 and 2. If I did that again, 4 bits 5 and 6, I see they look the same, they're just sort of shifted by a little bit more of an angle than 3 and 4. So I should see the same thing happen. The component may just be a little bit of a different size, but it should still point to the right. And then I do that with bits 7 and 8. And again, maybe a different size, but same idea, should point to the right. And so we're getting a field that's just adding up bits and bits and bits to the right. And that's going to go on all the way up until we reach this point at the center of the rod. And then it definitely creates a field that points to the right. So the overall field should point to the right.
I can tell even if it's like going in opposite directions, they don't. Because I noticed that here, or questions like these, that even if they're going opposite directions, sometimes they don't cross out. Like in this case, 1 and 2 don't cross out. So
1 and 2 do cancel each other out.
yeah, but I'm saying like for I think that's for E4 and E3.
Oh, why
They don't
don't
look
they
like they
cancel
would
out?
cross out. Yeah.
Because they're not actually in opposite directions. They kind of are. They point sort of the opposite way from each other. But what would really be the opposite of, say, this is E4, and I'll redraw it over here. What would be the opposite of that is this vector. Negative E4. E4 but flipped over. Those two cancel each other out, for sure. But that's not what's going on here. E3 and E4 are sort of pointing in the same direction if you think about just left or right. They're pointing opposite as far as up or down, and that's what sort of tells us we should look at those two pieces separately because they're doing different things. The left or right bit for each of them is they both point to the right. The up or down bit is what's different. E4 points up, E3 points down, and those parts cancel. But these parts sort of reinforce each other to get a net field that points to the right.
Will there be any questions regarding stuff from chapter 26.2 where it talks about resistivity and resistance from like temperature coefficient of resistivity?
No temperature dependent stuff, just the resistance is rho L over A, like was on the last exam with the heater wire in the car window.
Okay.
Yeah.
And I'm assuming we're gonna do also torque from on a current loop.
Uh, nah, it'll just be the force on a wire, straight wire.
Okay.
Yeah.
Thank you.
Yeah, I mean, all that stuff, it's not to say it's not important. It's just exams are supposed to be these really cut and dry things that just address sort of the main topic of each chapter, and that's all I care for them to be. The notes themselves are what I hope y'all take away from the class, and that's why I wanted you to have like a copy of them. Um, but yeah, for this, it's meant to be just a like pretty straightforward. Here's the main bit from this chapter. Did that make sense? Here's the main bit from the next chapter. Did that make sense? And so on and so forth.
You said to just like make sure we review the past exams too, right? Not just the practice.
Yeah, I would say probably just for the sake of time, since the practice is such a huge document and you've already looked at it for past exams, the exams themselves may be a better thing to start with to set the stage for what you might expect for the final. It won't be identical to them, but I am going to try to make it similar. And speaking of that, I said it in the email I sent out shortly before this, but exam 3 corrections are due tomorrow. You can bring them by my office at any time. You can send a scan over to me by email, however you want to get them to me, but I do need them by tomorrow for anyone who's going to submit them. Because I got to get that key posted for everyone to be able to study over the weekend. I can't really stretch out that due date. Other questions?
You said we would cover RC circuits, correct?
Yes.
Uh, could you do one question regarding the equation where we use that charging time?
Sure. Um, let's go to. Actually, let's. Yeah, I'll give a freebie for anyone who's going to watch this far for the exam corrections. Let's look at the one that was on the exam, because that sort of covers a lot of this stuff. So, a 12-volt battery, I'm going to label as I go, this is V0, is connected to a 10 ohm resistor, that's R, and a capacitor of unknown capacitance. So, I don't know that value. When the switch is closed, the capacitor takes approximately 0.5 seconds to reach full charge. It might be tempting to write tau for that, because that's the main time thing we looked at in this chapter, but we got to remember tau is this weird sort of thing for 63% of full charge. It's sort of arbitrarily defined just to make the math work out nicely with that exponential stuff. So really, I don't have a name for this variable for the total charging time, so I'll just call it T charge like I did in the hint during the exam. So T charge is related to that thing tau because we remembered that it takes 5 time constants, 5 tau, to reach full charge. And so tau itself is T charge over 5, 0.5 seconds over 5, or 0.1 seconds, which is the hint that was given. But let's see what we actually need to do. How much charge accumulates on the capacitor? So that's saying for full charge, how much charge is that? Full charge, we use Q0 when we're talking about RC circuits. The only equation I know, well, I guess there's two, so let's write both, that has Q0. Is this one that's just a general expression for charging time, and then this one that relates that max charge to the battery voltage. This is your general expression for any capacitor, but also for in RC circuits. So if we come up to the equation sheet to see where that is, it's really this equation, the very first one, but it's also sort of hidden in this expression. because you see Q0 over RC is the same thing as V0 over R. The only way that can be true is if those two are the same thing. So those are my options. The nice thing about full charge is it's what happens after a really long time has passed, meaning this whole thing it goes to 0 because you want it to be the case that Q equals Q0, which is only true if all the other stuff, all this E stuff, is not there. That happens when T goes technically to infinity. It actually takes an infinitely long time according to this equation, and that's why we have our rule of thumb. But that's what full charge is Q reaches Q0, which is equal to the capacitance of the capacitor times the voltage across it. So all I need after that very long-winded explanation is this equation. The problem is, I have V0, I don't have C. And so I need to come up with a way to find that capacitance C. Well, then I look at, well, what was the point of this thing up here? I remember that the time constant itself can be determined from the resistance and the capacitance. That's the idea that if we're looking at the water tower sort of analogy, the narrower the pipes, or the bigger the water tower, the more capacity it has, the longer it's going to take to fill it up. Because the pipes are blocking water flow, the capacitor is so big that you can put a lot of charge in there. So, if we look at that and the fact that we know that time constant, we can say, well, C is just that time constant over R. 0.1 seconds over R was 10 ohms. So that's 0.01 farads. I saw people put microfarads a lot just because you're used to seeing that for capacitors. But you got to remember, if we're in SI, which seconds and ohms are, then the unit that comes out is also the SI unit, not any prefix sort of thing. So it's also farads. And so capacitance is 0.01 farads. We can put that in up here. And the voltage was 12 volts. So 0.12 coulombs is our unit for charge. And that sort of juggles all the main things I'm expecting you to know about RC circuits as far as calculation. Conceptually, I could ask things like I did on this exam about the current, or the voltage, or any other thing. What happened to it over time? The current must have decreased for this one because the capacitor stops charging eventually. If current flowed continuously, you'd have a capacitor that kept filling up and filling up and filling up forever. It's an infinite water tower. That's not what happens. So the current has to decrease because charge has got to stop flowing eventually for the capacitor to be fully charged. That's what full charge means. And so that one's sort of you might call it a continuity argument. You can make similar arguments for voltage across the capacitor. It's filling up with water. If it's the water tower, voltage is the height, so the voltage is going up across the capacitor over time. It's going down across the resistor because if you think of like Kirchhoff's rule, the voltage is being supplied by the battery and then being shared between the resistor and the capacitor. So if the voltage across the capacitor is going up over time, it's filling up, there's less left over for the resistor. It's going down. And that's consistent with the fact that the voltage across the resistor is current times resistance, and this thing is going down because the capacitor is filling up. So all those trends are potentially questions I could ask, but stuff along the lines of these two questions. Any other questions? All right, if there aren't any, we'll probably go ahead and call it here. I will say, for the previous exam reviews, you might have noticed they're usually shorter than it actually took for the review. That's because I edit them down to try and cut out like long pauses or any of my mistakes. This one, it may be a little less polished just because I am scrambling to get a different exam ready. So this one may go up almost as the original file, and so feel free to play it at 1.5 speed or whatever you need to do to make it through. feel free to email any questions that you come up with over the weekend. And enjoy your weekend. I'll see y'all on Tuesday, 8 a.m. for the final exam, where, again, you can have front and back on this cheat sheet. So use that however you want to use it. I would recommend that table I mentioned earlier, though. It can really help with just playing the game of exams, because it's just it's a logic puzzle more than it's actual physics for these exams.